So this is a review from previous class, but because it's very important, and in my opinion, it's at the core of statistics, I will present these few slides again. So the idea is we have P samples, right? We have P samples, and these are independent samples, right? So what does independent mean? For example, if I'm sampling, students from Concordia, it means that I won't sample the same student twice, right? So in this case, these are independent samples, right? Now, these are all from the same distribution, so expected value of xi is constant, right? So xi's are different, but the expected value is the mean, right? That doesn't change. And the variance is also the same because it's the variance of the distribution, right? So the idea is that we define y as a new random variable, right? So if you haven't, if you missed the class on Wednesday, I think this slide is self-explanatory, right? You should be able to follow, right? The idea is that I'm taking P samples from some distribution, right? So this distribution can be, for example, like a new engine that has been manufactured, right? And, I'm measuring, the torque of this engine, right? So the expected value for all of the, torque measurements is the same. It's the average torque of this new engine. And the variance is also the same. It's the variance torque of the engine. Now, what I do is that I define y as basically the summation of those P measurements or those P samples divided by P, right? So I don't mention it here, but we can clearly see that y is the mean, right? Y is the mean of those measurements, right? Now, I proved in the previous class that expected value of y is mu, right? That means that the average, right? When I take the average of these, the expected value of the average, right? So note that there are two sort of averages applied in this operation, right? First one is y itself is an average, and E expected value is an average operator, right? So it's sort of like an average of the average, right? So that expected value is mu, right? And it is very intuitive, right? If you measure something 10 times and average the results, the average of the average is still the same as the average of the original sample. The average doesn't change, right? So this is, the first one is a little bit boring, but the second one is quite interesting. The second one is telling us that the variance of the average is P times smaller than the original variance, right? And that's very, very significant. And that's at the core of statistics, right? That's in fact how, the society works, right? Like scientific work and engineering work is based on. When you want to be more certain, you repeat an experiment a couple of times, right? The underlying reason for that is this equation, that when you repeat an experiment P times, the variance gets divided by P. And that's very important, because variance is usually something that we don't need, right? We usually try to avoid the variance because we like certainty. Like variance always tells us, oh, it's very uncertain, right? Okay. So that might be a bit dry to give you a tangible example. Let's look at this example that we did in the previous class. So average height of Canadians is 169 centimeter. And I looked up Wiki, it doesn't say the variance, right? So I made up some variance, right? So assume that the variance is 25 centimeters squared, right? Or in other words, the standard deviation is 5 centimeters, right? Now, let's look at this class, right? There is 108 students in this class. Let xi denotes the height of, all the students in this class. From 1, there's 108 students in this class, to 108. Right? So based on this statistic, right, we know that the expected value of xi is 169. Right? We don't have any other information. We know that the average height of a Canadian is 169. So we say that if we randomly sample from this class, the average height is 169. And this is also comes from the question. The variance of the height is 25 centimeters squared. Now we assume that the heights are independent, and I'm going to use the equation in the previous slide. Right? So I'm going to define y as the summation of the height of all 108 students divided by 108, so that this is the average height, right? This is usually denoted as x bar. The question is, what's the mean and variance of y? Right? What's the mean and variance of x bar? So what's key here is that since these x's are themselves random variables, that means that y is also a random variable, right? And because of that, y has a mean and a variance, right? So according to the equation from the previous slide, expected value of y is 169. The expected value doesn't change. But what's very interesting is that the variance does change, right? Now the variance of y is 0.23 centimeters squared. Much smaller than 25, right? And that's very, very important, right? That means that if we look at the height of one person, the height might vary a lot, right? It can be like 160, it can be 180, right? But if I take everybody's height and average that, the average is not going to be 180. The average is going to be 169 plus minus a small number, right? That's what it means. And I think that's very intuitive, and I think you agree with that, even before studying this course, right? So in other words, if I plot x looks like this. So this is the distribution of x. And this is 169, right? What is the distribution of, so if I plot x bar on the same graph, how does it look like? It's the same mean, right? But much smaller variance, right?
It's sharper.
Exactly. It's a much sharper normal distribution. So it looks like this. So it drops to 0 much, much faster. So, something like this. This is y, or x bar. Okay? So y has much, much smaller variance. And I hope that's clear, because this is the core idea of the rest of this basically course, right? Chapters 8 and 9 and 7 is all about this. Any questions? Okay, all right. Okay, so far in the book, we assume that we can somehow model the population, right? For example, we were playing with the deck of cards, so we knew exactly how many cards there are, so we could calculate, probability of different things. Or we were throwing, dice, so we knew, what's going on, right? We knew the mechanics of the problem, right? But very often, the mechanics are very hard, to mathematically model, right? So for example, the stock market, right? We can't really formulate it as a closed form mathematical equation and say, oh, this is this distribution, right? Or let's say you develop a new combustion engine, right? It's very hard to, exactly write down the equations for this combustion engine and at the end calculate the average torque and, variance of the torque and whatever, right? So in those cases, what you do is that you measure, right? You measure a few times, and based on those measurements, you sort of guess what's going on with this system, right? And that's the concept of population versus sample, right? Sample means that we don't really know what's going on, right? So the system is a black box for us. So we keep taking samples from the black box so that we understand what's going on. And population means that, we know exactly the details of the system. We know the mechanics, like, for example, we are playing with 5 decks of cards. So I can write down the mathematical equations of what's going on, right? So the notations are also different. So when we talk about population, the mean of the population is denoted with mu. And the number of samples in the population is normally denoted as a capital N, right? And the variance is usually denoted as sigma squared, right? So this is the case if we know everything about our problem. Right? For example, we know that our population is a binomial distribution with a mean of something and some variance. Now let's look at an example. Assume that we have 5 values for our random variable x, and it's important to note that these 5 values contain the entire population, right? Meaning that it's we have made like a special edition of a car, and there's only 5 of them. We're not going to make any more, right? That's done, right? So it's basically the entire limited edition contains 5 cars, right? So let's say our samples, basically those 5 values are 0 to 4. Sorry, not samples. Basically, the members of the populations are 0 to 4. Right? So let's say these are the weights, right, or the heights. So from 0 to 4. So from these 5 measurements, we can calculate mean, and the mean is going to be 2, right? It's the summation of all divided by 5. And we can calculate the variance according to either equation. This is the definition, and this one, we can prove that these two are equal, but this one is almost always easier to compute, right? So using the definition, basically, the variance is going to be the first number minus 2 plus the second number minus 2 plus the third number minus 2 plus so forth. So we get a variance of 10 divided by, basically, using the equation, is summation of these divided by n, right? So it becomes 10 divided by 5, that's 2. The other equation that we gave in the previous slide is the summation of xi's squared divided by n, and then minus mean to the power 2. So this will be 0 to the power 2 plus 1 to the power 2 plus 2 to the power 2 plus 3 to the power 2 plus 4 to the power 2 divided by n minus mean. This is mean, right? Mu squared. And we get the same answer, 2, right? As you have probably guessed, this is a very unrealistic case, right? It's very rare that we have like a limited edition of a car and there's only 5 of them, and there's nothing more. Usually interesting things, have more, basically, have bigger sizes, right? So, for example, if we look at the population of Canada, it's a large number, right? So this equation that we gave in the previous slide for the mean and variance sort of are useless because, for example, mean is sigma xi divided by n, right? So to calculate the mean of the population of all Canadians, I have to go and measure everybody's height, right? Which is not realistic. So instead, what we do is that we rely on a small sample, right? Because we rely on a small sample, the problem is different, right? So the big circle here is the entire population, right? And we denote the mean of the population as mu and the variance as sigma squared. But because this entire population is so large that we can't calculate all of the x's, that means that we can't really calculate mean and variance, right? We can't calculate mu and sigma squared, right? Because of that, we rely on a small sample, right? So we take 50 samples and we calculate the mean, right? So now we denote the mean as x bar, not as mu anymore, right? So that's the first distinction that you have to remember. It's very important, right? And it's not just, for this course, this is like a common notation, right? When you rely on samples, we denote mean as x bar, not as mu. And we denote variance as s squared, right? And that means that this is not the real variance of the population. We have calculated it based on some samples, right? So this is very important distinction, right? S squared and x bar, and here we have mu and sigma squared. Any questions? Okay. So let's look at the equations for x bar and s squared. So the equation for x bar is the same as the mean, right? So you add up all of the x's and you divide by n, right? And when we compare that to the equation for the mean, we see that it's the same equation, right? The mean of the population, right? So that's also xi divided by n. Right? Of course, we have to note that, n, capital N, means that all of the, samples in the population, and small n means the number of samples, right? So always small n is smaller than capital N. Right? But the equations look quite similar. Any questions? Okay. So let's look at an example, right? So let's say that we have a new engine, right? And we have made 8 measurements from this engine, right? And these 8 measurements are of the pull-off force, right? They are written here. Right. So, and also they are basically denoted here in this basically scatter plot down here, right? So this is the force, and these are our basically measurements, right? So based on these measurements, we can calculate x bar, and x bar is going to be 13 pounds, right? So in average, this engine calculates, 13 pounds of pull-off force, right? So we will link this later on to mu and, sigma, right? So basically what we will do in a little bit is that we will show that the expected value of x bar is mu, right? That means that this basically number that we calculated, 13, right? We don't know the entire population, therefore we don't really know mu, right? But we can say that whatever x bar we calculated, right, the expected value of that is actually mu, right? So mu is basically close to this number, right? So in fact, mu is close to x bar, right? We can say that that's what this equation means. So we will basically talk about this later, maybe today or maybe on Wednesday. Okay? So this is very easy. Yeah?
So here you're saying the expected value of x bar is equal to mu, but you said x bar is actually like the mean when we take a sample. But how can we do the E of x bar?
Yeah. That's a very good question. That's a very, very good question, right? And this is a very confusing, basically, subject. I have a few more slides to talk about this, but now that you asked this, I can mention that. So basically, what is basically confusing is that x bar here is a random variable. Why x bar is a random variable? Because x bar changes depending on the sample, right? So one time, I could have picked these samples. If I sample again, I might take these samples. Right? So that means that x bar changes, right? So and that's a very confusing concept. I have a few slides to talk about that, right? But, in addition to the notations being different, right, these are also different concepts, meaning that mu is a constant value, is not a random variable. Mu is mu, right? It's the entire population's mean, right? But X bar is a random variable. It can change, right? Next time you can sample some other 8 numbers, right? And that's why I wrote here expected value of X bar is mu, not X bar equal to mu, right? Yeah?
What if we say in a problem we have different samples? How can we differentiate X bars? Is it going to be X bar A or
Yeah, we can do that. Yeah. So let's say, you make 8 measurements now, you calculate X bar, you make another 8 measurements, so you have X bar 1 and X bar 2, right? And you can have X bar 3, which is the average of all 16, right? That's in fact a better measure for X bar if you average all the 16 values. So these will become clear later on, I hope. Any other questions? Okay. Right. So you guys asked very good questions, right? So by this time, these things, become clear much later, right? Usually at this stage, students are very, very confused, but these were very good questions. Okay, let's continue. So the variance is a little bit different, right? You probably have seen that variance is always a little bit more tricky. So the equation for the variance S squared is X bar, Xi minus X bar to the power 2. So this part is the same as before. But what's different is that instead of dividing by n, we divide by n minus 1, right? And that's the mistake that many, many people make, in real life. They divide by n, not by n minus 1. And that's, if n is small, that's a big difference. So for now, just accept this equation. I will show intuitively why this is the case, why we have to divide by n minus 1. Okay, so let's look at the same example that we just looked at, right? So we have 8 measurements of the pull-off force, right? So these are the 8 measurements. And the sum is 104, and divided by 8, we get 13, so that's X bar, right? So this is from the previous slide. Now we want to calculate basically S squared, the variance of the samples, right? So what we do is that we use the equation. So this is equal to sigma xi minus X bar to the power 2 divided by n minus 1, right? So this row here shows xi minus X bar. So for example, 12.4 minus 13, that's minus 0.4, right? So we write all of the values here. So 12.9 minus 13, that's 0.1, right? So we write all of the values for this column here. And then we have a square operation here. So we square them here, right? So 0.4 to the power 2 is 0.16 and so forth, right? And we apply the sigma operation here. So this is the sum. So this becomes 1.6. Right? And we divide by 7, not 8, right? We basically divide by 8 minus 1. And we get S squared, which is 0.2, right? So you can tell that if we divide it by 8 instead of, 7, we would get a smaller number, right? Instead of 0.22, we would probably get 0.2. Or 0.19, something like that. And that's incorrect. Any questions? So you see the concepts are a bit, abstract and confusing, but at the end, once you get them, it's you just follow a certain steps. Again, in my opinion, these are much easier than chapters 2 and 3, once you get the concept. Okay. So same as the equation for the variance of a population, the variance of a sample also can be simplified, right? So this was the original equation, right? And it's straightforward to prove that that equation is equal to this one. And this one is easier to compute, the one at the end. right? So this means that square each one of them and then sum them. And then you have also calculated the sum before because you wanted to calculate the mean, right? So you already have this, right? So this was already known. All you have to do to calculate s squared is to square each one of them and then add them up, right? So let's look at an example. So here we have the same 8 measurements that we had before, right? In order to calculate x bar, I have to calculate the sum. So the sum is 104, right? The sum of all these measurements. And now, to calculate basically this term, I square each one of these. So this one is squared. 12.6 squared is 158. 12.9 squared is 166, and so forth, right? And I add all of them up. At the end, I get 1353. So this number is 1353.6. And I had already calculated the mean that was 104. So this number down here is 104, right? So basically, I will have 1353 minus 104 to the power 2 divided, here is n, right? So when you use this equation from the crib sheet, you have to be very careful because here you have n, and here you have n minus 1, right? So at the end, we get the same number, right? 0.2286, exactly the same as before. So the variance of these samples is basically 0.22. Any questions? Okay. So I will try to explain why we divide by n minus 1, not n. Right? So what I'm going to do now is not actually in the book and not in the course, but I think it's quite important to know why we divide by n minus 1, right? So basically the idea is that if we somehow magically know the actual population mean, then we have to divide by n, right? So s squared is equal to xi minus mean to the power 2 divided by n. But this equation is simplistic because usually mu is unknown, right? We don't know the mean of the population, right? Because of that, what we do is that instead of mu, we use x bar, right? But how do we calculate x bar? We calculate x bar from the data itself, right? So, if any of you is, working in robotics, there's a concept called degree of freedom, right? That means that like how many different, different types of motion some object can have, right? So like motion in the x direction, in the y direction, in the z direction, and 3 rotations. So for a rigid object, that's 6 degrees of freedom, right? That concept also exists in statistics. When you make n measurements, right? We say that we have n degrees of freedom, meaning that each one of those n values can change, right? But when you use those n values to calculate x bar, you sort of pin down one of them, right? So you use n data to calculate one value already. So you lose 1 degree of freedom, and because you lose, you essentially lose one of the measurements due to, for measuring x bar, you divide by n minus 1, right? So that's the normal, explanation that's given for y divide by x minus 1. There's something that, there's one explanation that I think is better, and that's my own explanation, right? So always when you try to basically explain something, it's easier to explain it at the limit, right? When things are very, very easy, right? So for this case, the limit is when we only have 2 measurements, right? So let's see how we calculate the variance if we only have 2 samples, right? That's a very extreme case, right? that means that we want to estimate the variance of a sample based on 2 measurements only, right? Because with 1 measurement, it's impossible to calculate the variance, right? You only have 1 measurement. How do you calculate the variance? There's no way to do that, right? And again, since we want to explain this, right, we like to make our life easy. So assume that the 2 measurements that we have are -1 and 1, right? So why did I do this? Because I want x bar to be 0. It just makes our life easier later on, right? So let's say we were measuring something, and our 2 measurements are -1 and 1, right? So if we look at the previous slide, right, we have 2 basically equations for calculating s squared. One of them is xi minus mu to the power 2. The other one is xi minus x bar to the power 2, right? So I call this numerator 1, right, from the equation 1. And I call this numerator 2 from equation 2, right? So this is numerator 1. This is xi minus population mean. This is numerator 2. This is more useful because I don't know population mean. So I replace that with x bar. Right? So when we calculate x bar, we see that x bar is 0, right? So this is 0, right? So this becomes 1 to the power 2 plus 1 to the power 2, and that's 2, right? So this guy is 2, right? This guy is unknown because we don't know mu. Any questions so far? Okay. How many people have no idea what we're doing? It's like completely lost. It's okay if you raise your hand. Okay, all right, quite a few. Okay, so I will explain from the beginning, right? Let's say I'm measuring something, right? Like a pull-off force of an engine, right? Or a current, right? And let's say I only make 2 measurements, right? My measurement 1 is -1, so x1 is -1, and x2 is 1, right? So it's similar to the previous example where we had 8 measurements of that engine, right? I wrote down the 8 measurements that I had in terms of force, right? But here I wanted, to be able to explain a concept. So I intentionally wrote x1 and x2 such that the mean is 0. It just makes our life easier later on for the equations, right? So it's a very simple, case. I have 2 samples, only 2 samples, right? And the reason I'm doing this is that, the fact that I'm dividing by n minus 1, right, is not really important if I have 100 samples, right? If you have 100 samples, it doesn't really matter if you divide by 100 or 99, right? At the end, you get only 1% error, which is quite small, right? This becomes important when you have few samples, right? For example, 3 samples or 5 samples, right? And, n can't be 1 because if it's 1, I have a 0, right? So the smallest number n can be is 2, right? So that's why in my example, I'm setting n to 2, right? So that I can see the difference between dividing by n minus 1 and n, right? So if n is 2, then you get one of them is 2 times bigger than the other one, right? If you divide by n or n minus 1, right? So the difference is huge. Okay. All right. So I can calculate this numerator 2, and that number is 2, right? But the issue is that if you have 2 measurements, -1 and 1, right, it's not guaranteed that mu is 0, right? Mu can be any number. Mu can be here, mu can be here. You might have been unlucky and mu could be here, right? Like the actual mean of the population could be like -1.1, right? And when you take 2 samples, just randomly, one of them is -1 and one of them is 1, right? The actual mean can be anywhere. It's not necessarily 0, right? So the idea is that the actual mean can be anywhere, right? It could be, for example, 0.8 or 0.9, or it could be, even here, it could be like 2, The chance is low, but still it could be 2, right? It could be 0.8. It's not a very high chance, but it could be 0.8, right? So let's just see what happens if the actual mean was 0.8. So if I plug in 0.8 for me, then I can calculate numerator 1, right? And in this case, it's going to be 3.28, right? And this is much bigger than 2 that we originally had, right? This is almost double that, right? And in fact, I plugged in 0.8 because I didn't want to, write mathematical equations, but it's easy to prove that for any mu, numerator 1 is always bigger than or equal to numerator 2. It's always bigger. It can never be smaller, right? So that means that if I go back to this previous equation, what color we haven't used, this guy, right? It means that this guy is always bigger than this guy. Why? Because I'm using the data itself to calculate x bar, and that gives me the small value, right? And since the second one is always smaller than the first one, I divide by a smaller number so that I somehow, compensate for that, right? So basically, that's the idea. That's the idea of why we divide by, why we divide by n minus 1, not by n. Because the numerator is a little bit smaller, we compensate for that, and we divide by something that's also a little bit smaller. Now you might ask, why not divide by n minus 2? Or why not divide by n minus 0.5, right? Or why not multiply by something, right? Like multiply by, 1.1, right? So the mathematical proof, we will actually talk about it a little bit in this course. So we will prove that you actually have to divide by n minus 1. And if you're interested, this is a very, important concept. And it's a very important concept in machine learning, right? So if you pick up any machine learning book, they actually prove for you that that's the right way to calculate the sample variance, right? So this book, for example, has a good and intuitive proof for that. Any questions? Okay. All right. So the next concept, which is a much easier concept, is the range. So that simply means from the beginning to the end, right? So nothing fancy here. So the range is the maximum value minus the minimum value. So from those pull-off force, measurements, the maximum value was 13.6. The minimum value was 12.3, and the range is 1.3, right? One thing to note, that population range is always more than sample range, right? That means that, our samples were here. Let's say these were our samples, right? But that's not necessarily, the entire population, right? We might, if we repeat more, we might get like these samples, right? And one of them could be outside of this range, right? So the population range is always bigger than the sample range. And that's it for this chapter. Any questions? Okay. So just a quick note that in basically we cover 7.1 to 7.3, excluding 7.3.4, right? So in 7.3, we don't cover 7.3.4. So this chapter starts with the central limit theorem that we, briefly talked about before. It's a very, very important theorem, right? And in my opinion, this could be, the most important theorem that you study this year, right? Not just in this course, this year in general, right? And this theorem says that if you take n measurements from some population that has a mean of mu and variance of sigma squared, and you define x bar as the mean of these n values, right? then if you define z as x bar minus mean divided by sigma divided by square root of n, right? Z is the standard normal distribution, right? And it's a very, very important theorem. It basically, if you read it, it doesn't say anything about the original population, right? It didn't say that the population needs to be, you know, Poisson distribution or uniform distribution or binomial distribution or anything, right? If you start with any population, with any shape, and you average that, you end up with the normal distribution, right? And that's a very, very interesting concept, right? And in my opinion, a very strange concept, right? It means that, you know, let's say you had a weird population, right? So like you had some, you know, variable that was changing from, let's say, 50 to 60, right? And this is the PDF of that variable, right? So as you can see, it has a very strange PDF, right? The central limit theorem tells you that if you take n samples from this, right? And n, by the way, needs to be large. For the sake of this book, we assume that n is more than or equal to 40, right? So if you have 40 samples, we say that is big enough, right? So if you take 40 samples from this guy with a weird distribution and you average them, you end up with a normal distribution. Right? So that's basically the central limit theorem. Any questions? Okay. And that's why the normal distribution or the Gaussian distribution is very important, right? Because if you have enough samples from any distribution, that becomes Gaussian. Okay, so let's look at an example. So we have a random variable x that has a continuous uniform distribution, right? So f of x is x is between 4 to 6, and is 0 otherwise, right? So we can quickly check whether it's a valid PDF. If we take the integral of f of x from minus infinity to infinity, we get 1, right? So it's a good PDF. And it's also always positive, right? So we take 40 samples from this distribution, right? What does that mean? We take 40 samples. For example, if you're using, you know, MATLAB code, right? Then it means that you basically sample from, I think in MATLAB is RAND. RAND gives you random numbers, you know, between 0 to 1. And they are uniformly distributed, right? Meaning that the probability of getting, you know, any number in the range 0 to 1 is the same. Probability is 1, right? All numbers have the same probability. So taking a sample size of 40 means that running this code 40 times, right? Taking 40 samples from that. And you calculate the mean, the average of those 40 numbers, right? We want to know what's the distribution of this new thing, right? So basically we have x1 all the way to x40, and I calculate x bar, which is the average of those, and I want to calculate the distribution of x bar, and the distribution of x itself was as follows, right? So x was from 4 to 6, right? And this number is 1 over 2, right? So the central limit theorem tells us that x bar is a Gaussian distribution, right? Because we are averaging 40 samples. Okay. So this is the original distribution. It's from 4 to 6. To use this equation, right? Remember that we had z was x bar minus mean divided by sigma divided by square root of n, right? So we need to calculate mean, and we need to calculate sigma, right? And n is 40, right? So the mean of a uniform distribution from the crib sheet, it's 4 plus 6 divided by 2, that's 5. And it does make sense. The mean is right at the middle. And the variance, again, from the crib sheet, note that here we write sigma squared, not s squared, because it's population, right? It's from our original population that we knew was uniform. The equation was b minus a to the power 2 divided by 12, and that's 1/3. Right? So now I know everything is this equation. I know mu and I know sigma, right? So I just plug in. So sigma, for example, my new sigma, right? So this guy becomes 1/3 divided by n, which is 40, so that's 1/20. Right? So this is my new, basically, sigma. Right? So this thing, the denominator, so if I go back to the previous slide, so when this is the standard normal distribution, another way of writing the central limit theorem is the following. X bar is normal distribution with a mean of mu and standard deviation of sigma divided by square root of n, right? These two are equivalent, right? Saying that Z is the standard normal distribution and saying that X bar is a normal distribution. Note here, I'm not saying standard normal. It's just normal, right? Now this should be clear to you that these two statements that I have boxed are equivalent. Is there anybody who doesn't see why these two statements are equivalent? It's okay if you raise your hand. This is from previous chapter. So in fact, this was the transformation. So this was the transformation to make any normal distribution standard normal, right? Minus mean divided by standard deviation. Okay. So in fact, in this example, I'm using this one, right? I'm using this box version. So basically, I'm saying that X bar has a mean of mu and variance of sigma squared divided by n is equal to, I think sigma squared was 1/3 divided by 40. Right, so I'm using this basically version of the central limit theorem, that X bar has a mean of mu and variance of sigma squared divided by n, or standard deviation of sigma divided by n square root of n. Okay. And if we calculate that, that's 1/20, right? So when you look at, so this is very important, right? This is X bar, this is X. When you look at the distribution of X is very spread, right? 4 is as likely as 5, as likely as, basically, sorry, 4 is as likely as 5, as likely as 6, right? So when you sample something from this, the chance of getting a 4 is equal to the chance of getting a 5 is equal to the chance of getting a 6, right? But what's very cool is that when you sample from this, it's very, very unlikely to get a 4, right? What does that mean? That means that if you take 40 samples from this distribution, it's very, very unlikely that all of the 40 samples are 4, right? That's what it means. And I think that's intuitive to you guys. So that means that if you take 40 samples, those 40 samples are most likely going to have a mean of 5. Right? So you can see that it's a very much sharper distribution around 5. Any questions? Okay. So we did see central limit theorem before, right? I think this is like a more tangible example, right? When we roll a die, right? So if we roll one die, probability of getting 1 to 6 is 1 divided by 6 is a constant number. Now, if I roll 2 dice, right, it becomes a triangular distribution, right? So the number in the middle has the highest chance, right? And already, you know, at 3, so if you, so next one is 3, right? Already at 3, we see that, oh, it's starting to get the shape of a Gaussian distribution, right? And when we increase it to 5, it's already, you know, very, very Gaussian. So in fact, we don't really need 40, you know, even less than 40, it looks like Gaussian, right? But, you know, for this course, we always use 40 as the threshold. Any questions? Okay. So this is a link to a video that you can actually see this physically, right? So all of the concepts that I talked about so far were like averaging, you know, like let's say running a code or things like that, right? This was a cool physical example that I saw, right? That somebody actually built a device, right? And this device has a lot of small ball bearings, right? And they all accumulate here, right? And when he flips it, each one of them, you know, basically hits these pins. And when it hits a pin, it can go to left or right, right? So each one of these balls can end up anywhere here, you know, from here to here. But when you look at all of them, since there are so many balls, right, most of them end up in the middle, right? And there is proof that, you know, this is also a normal distribution, right? And it is related to the central limit theorem. So I'm not going to play the video here because the recording will be, you know, damaged. But I do suggest you watch the recording. He does it a few times, and you can see that every time is quite similar to this curve. Any questions? Okay. So the next basically equation is when we have two distributions, right? So we have population 1, which has a mean of mu1 and variance of sigma 1 squared. And we have population 2 that has a mean of mu2 and variance of sigma 2 squared, right? And let's say I sample from population 1 and I call the average x bar 1, and I sample from population 2 and I call that x bar 2. Then this equation, z, which is x bar 1 minus x bar 2 minus the difference of the means divided by the first variance divided by n1 plus the second variance divided by n2 is basically standard normal. If the conditions of the central limit theorem apply, and that means that n is large, right? And so for the sake of this course, is if n is more than or equal to 40. And if the two populations are normal, then it actually does apply. It's not approximate anymore. So n doesn't need to be large anymore. Right? So it looks like a large equation, right? But hopefully with an example, it will make sense. It's not that as complicated as it looks. So let's look at an example to see actually what this equation means. Okay, so the effective life of a component used in jet turbine aircraft engine is a random variable with mean of 5,000 and standard deviation of 40 hours, right? So in average, it lasts 5,000 hours, and the standard deviation is 40 hours. And it is close to a normal distribution. The engine manufacturer introduces an improvement into the manufacturing process for this component that changes the parameters to 50-50, right? So it increases the life from 5,000 hours to 5,050 hours, right? Increases the life by 50 hours. And it reduces the standard deviation from 40 to 30, right? So overall, it's a very good improvement, right? Because it does increase the life, which is good, And it also decreases the standard deviation, which is also good. So we take 16 samples from the first component and 25 samples from the second component, right? And we want to know what's the probability that the difference in the two sample means is at least 25 hours, right? So if I recap the question, the new component has a life of 50 hours. The old component had a life of 5,000 hours, right? So in average, the new component has 50 hours more life than the previous one, right? Now I'm sampling some from this component, I'm sampling some from this component. And I want to see what's the probability that the average of these samples is at least 25 hours more than the average of these samples. Right? For example, it's 30 hours more, or 40 hours more, or 50 hours more, or 100 hours more, right? So at least 25 hours more. So it's good to summarize the values that we have so far. So for component 1, I have a mean of 5,000 and standard deviation of 40 hours. For component 2, I have a mean of 50 and standard deviation of 30. I'm taking 16 samples from this and 25 samples from this. Right? And I want to use this equation. That's also included in the formula sheet. Right? So the first thing, let's attack the biggest part, right? The biggest part is the denominator, right? So sigma 1 squared plus sigma 2 squared divided by n1 plus n2. So that's going to be equal to 40 to the power 2 divided by 16 plus 30 to the power 2 divided by 25, right? So this is the numerator, right? And now the next thing that I need to calculate is mu1 minus mu2. So mu1 minus mu2 is 5,000 minus 5,050, so that's minus 50. Right? So mu1 is 50 less than mu2. That's what this equation means. Right? So again, going back to x bars, right? Remember that x bars here are random variables, meaning that they change, right? Depending on which samples you have selected, x bars change, right? So if I plot, so let this axis be x bar 1 minus x bar 2, right? So this is going to be a normal distribution with a mean of, or did we lose? Yeah, I guess we did lose. So the mean was minus 50, right? Because this guy here, mu1 minus mu2 is minus 50. And some standard deviation, right? So this is the standard deviation of this thing, right? So basically what we want, we already calculated this, right? So I wrote it here, but we didn't calculate the actual number. But it's easy to compute, right? So we want the average life to be at least 25 hours. So this is, let's say this is 0, right? And this is minus 25. Right? So basically what I'm interested is area under this curve here, right? Because if x bar 1 minus x bar 2 is minus 50, I'm happy. That's more than 25 hours. If it's, minus 40, I'm happy. If it's minus 60, I'm happy, meaning that it satisfies this condition, right? So I'm interested in area under this curve, everywhere from minus 25 to minus infinity, right? And basically, and it is quite straightforward to calculate this area under the curve, because I know the variance and I know the mean, right? So all I have to do is to make it the standard case, right? So once we basically plot this curve, it's done, right? The rest is looking at the table. So the solution that I provided here is a little bit different from the solution that is in the next slide, meaning that I assumed X1 is the first engine and X2 is the second engine, right? But it's symmetric. You can assume X1 is either engine and X2 is the other engine, right? So in the solution that you see in the next slide, it's probably a little bit easier because in the next slide, we assume that X1 is the new engine and X2 is the old engine. And because of that, what happens in the next slide is that the distribution becomes like this. It becomes positive. Instead of minus 50, it becomes plus 50, right? And since it's plus, it's a little bit easier to work with. So let's look at the next slide, right? So, so basically, this is x bar 2 minus x bar 1, right? And here, basically, if I go back, what I plotted here was x bar 1 minus x bar 2, right? Actually, no, in both of them it's the same. No. So what I wrote here is incorrect, but the rest of it is correct, right? So what I plotted here is x bar 1 minus x bar 2, and you can see that it's negative, right? Because x bar 1, the old engine, has a lower life than x bar 2, and because of that, the mean life, the average is negative, right? But in this solution, we plot the negative of that, meaning that I plot x bar 2 minus x bar 1, and that is going to have a positive mean of 50, right? But the area under the curve is the same area. I'm interested in this area, and the rest is, super easy because all I have to do is that I have to do 40 divided by square root of n, which is 4, plus 30 divided by square root of 25, which is 5. This to the power 2 and this to the power 2. So this is my new variance. And this is going to be, so 40 divided by 4, that's 10 to the power 2 is 100. So that's 100. Plus, this is 6 to the power 2 is 36, right? So that's 136. So that's my new variance, and my new standard deviation is going to be square root of that. And that's, I think this guy, 11.7, right? So the idea is that the mean is 50 and the standard deviation is 11, right? So once you know the mean and you know the standard deviation, the rest is trivial, right? All we have to do is we have to calculate the z associated with this number, right? So z becomes 25 minus mean divided by 11. And that's minus 2.14. And from here, we have to look at the table. For minus 2.14, I get a probability that is 98, right? So that means that there's a very, very large probability that the average life of the second sample is at least 25 hours more than the average life of the first samples, right? And it does make sense because if you remember, the second engine in average provides 50 hours of more life, right? So it does make sense that this area under the curve is 98. Any questions? Okay. I think that's the last slide. Yeah. Right, so we have about 9 minutes left, so we can, these are actually reviews, so it's probably good to do them now. So basically in this lecture, we talked about sample and population, right? Sample itself is a random variable, right? So x bar is a random variable and s squared is a random variable. So if I sample another time, you know, my sample could be here. So these numbers actually change. And very often, we cannot get the entire population. So if we look at average height of all Canadians, right? Or we have developed a new drug, right? It's actually unethical to test the drug on the entire population to see how it works, right? First, we always test it on, you know, 10 or 20 or, you know, so there are different levels of the trials, right? First, it's tested on, let's say, 10 subjects. When we see that it's working, then we test it on 100 subjects in the next phase. When we see that it's working, we tested it on, you know, 1,000 subjects. So we increase the sample size so that we get more and more definitive answers, right? But we never test something new on everybody, right? Or like quality control, right? Let's say you're doing some QC, right? It's very expensive to do QC on all the devices. So you do QC on some of them, right? Or let's say your QC destroys the device. So you can't actually do QC because you will destroy all the devices. Because of that, we take samples from the population and we infer statistics of the entire population from those samples. And we basically use those samples to calculate a point estimate for the population, right? So what does a point estimate mean? So this is a new concept. So a point estimate means a reasonable single value, right? For example, mean is a reasonable single value. And the randomness lies in the samples selected. The population itself is not random, right? So it's a fixed population. The population is not changing. The basically variability comes from the samples. Okay. And then we introduced the concept of the central limit theorem. So if we have n samples, then basically the second form of the central limit theorem will be x bar is normal with a mean of mu and a standard deviation of sigma divided by square root of n, right? So this statement that I wrote here is equivalent to this statement here. Right? So whatever the population was, right, whatever its mean and variance, the average is going to be a normal distribution. Any questions? Okay. All right, and we looked at this example, right? I really like this example because it really demonstrates what's going on, right? So the original distribution was uniform, but the mean has a normal distribution. So this is our population, right? This is the graph, and this is the PDF. And this is the sample. Right? You can see that population and sample are two different things, right? Our population had a uniform distribution, but our sample mean has a Gaussian distribution. Any questions? Okay. So one question. So what is the distribution of X? So here X is one sample that I'm taking. What's the distribution of one sample that I'm taking from this distribution? It's uniform, right? If you take one sample from that guy, the distribution of that sample is uniform. If you take two samples, the distribution of both of those samples are uniform. If you take 100 samples, the distribution of each of those 100 is uniform. But if you take the average of those 100, now the average is a different story. The average has a Gaussian distribution, right? And that's central limit theorem. Okay. And this was the last equation that we saw in this basically lecture. If I have two different populations with means of mu1 and mu2, and also different standard deviation, then the mean of samples x1 and the mean of samples x2, the subtraction of those two means is also a normal distribution. Any questions? Okay.